Okay. All right. So we're officially begun today. Welcome to everyone who is on Zoom. And of course, everyone's in class. So welcome. Remind me in a few minutes, if I forget, I might remember, but if I forget, remind me to pass out the roll sheet. I think is there anyone here? There's no one here that was not here on Monday, either here or online, right? So no one that totally missed class on Monday. I'm talking about physically here, not the online people. Okay, all right. So, when I pass this back around, you want to sign in the same slot that you signed last time. But if you were online and you and now you're here today, I still filled in your name as a 10. So look for where your name is, right, and sign in that slot. Okay, right. When I pass that, right. So I got the one from last time is attached, so you'll know where you sign, right? If you okay. All right. So I put so remember, next time we have this assignment due on entering answers in WebAssign. So and you can enroll right now free. So okay, I just we're gonna have to. You can enroll now in WebAssign right for free. So and that continues, I think, through next Wednesday, and then you will have to actually pay and register. And I think 28, as before I came to lecture this morning, 28 people had actually enrolled. So we're getting almost everyone. So if you have not enrolled yet, go ahead and enroll so you can work on that entering math answers homework, right? Because that's due on Monday. Okay. And then I now posted some more assignments. So our next assignment, which is really math content assignment on the coordinate plane, I posted that one. So we're going to be deeply into that material today. So you'll be able to begin working intelligently on that assignment. And now also, however, I posted an algebra review. Notice this is not due until the time of the first test, which is February 23rd. That's what it's scheduled to be in the syllabus. This is an optional assignment, right? And so you, by doing that assignment, if you get 80 on that assignment, you can get $10 of flux, okay, added to your flux total. All right, so it's worth $10 if you get an 80. So the purpose of that review is just to review for you some basic things from algebra that that are useful here in the class, but we're not going to really spend that much time explicitly talking about, right? I'm talking about very, very basic algebra skills. So that's
okay.
And so you have a lot of time to work on it until the first test, and then it's worth that $10 extra credit. But because it's optional. All right. Okay. Someone is that you, Alexander? Yeah. All right. Thanks, Alexander. Okay. So we've got stuff now posted for you. So you've got plenty to keep you busy, right? Okay. For your homework. Ahmad asked a question earlier about when we do get to that first test on February 23rd. He said, am I going to give you a formula sheet? And the answer is no, I will not give you a formula sheet. But what I will do is let you create what's called what I call a survival card. So that is an index card to put things on, right? That you can bring as whatever you need, whatever aids you need to help you with the test, right? But so this is purely the things that you're going to create, right? Okay, on the survival card. So it has to be an index card. It has to be a standard size index card, but that's any size. So it could be this size, okay, if you like, or one of the smaller index cards as well, right? Okay, so so as you're preparing for the test, you want to be creating your survival card, right, for the test. So things that you think are difficult to memorize, then you put on the survival card, right? Or examples of problems that you think might might be helpful for the test, right? Okay. Those things you can put on the survival card. So that's the what we have of a formula sheet, right? For test number 1. So I'll remind you about that when we get a little bit closer to the test. But there's the answer to your question. Yes. February 23rd, I think, is the first test. I looked in the syllabus when I was posting this homework, and it said, I think, February 23rd. But if that's not right, then tell me that, and so I can fix this due date, because I wanted this to be due at the time of the first test. So you'll be reviewed algebra by the time of that by the time of the test. Okay. But remember, you can do this a little bit at a time. Other things have sooner due dates, right? So you'll have to concentrate on those. So you'll have those done by completely by the time that they're due. Okay. All right. So don't think I have any other sort of class procedure sort of stuff. Let's go back to the, so we're going to just jump right back into the notes. Let's go back to the notes here. And I do have a little bit of an activity for you guys. It's easy one, though. It's not really a recall activity. If I can scroll here. I want you to, for me here to, on the graph paper, I want you to draw for me, don't make it too small, okay? I know some of y'all like to write things really tiny, okay? But I want you to create for me on the graph paper a triangle, an obtuse triangle. Now I need to tell you what an obtuse triangle is, right? With triangles, there are 3 types of triangles. Last time we were talking about quadrilaterals and parallelograms, right? Okay. Quadrilaterals are 4-sided, right? And parallelogram is a particular type of quadrilateral. But back to triangles. Of course, triangles are 3-sided figure, and you can categorize triangles in various ways. But one broad way of categorizing triangles is obtuse, right triangle, and acute triangle. So an obtuse triangle is a triangle that has an angle that's bigger than 90 degrees. Okay, bigger than 90 degrees. Okay. A right triangle, of course, is a triangle that has an angle that's exactly 90 degrees. So we're going to be working a lot with right triangles in class, less so with obtuse triangles. And then an acute triangle is a triangle where all the angles are less than 90 degrees. Okay. So on your grid paper, on your graph paper, I want you to draw for me an obtuse triangle, right? Just based on that definition. However, I want you to do it kind of carefully here. I want you to draw it so that the corners of the triangle, the vertices of the triangle, corners of the triangle are called vertices of the triangle. I want them to be at grid points, at grid crossing points, okay? Because that's going to make the activity that we're going to do with the obtuse triangle a little bit easier. That's what I mean by a grid point, right? It's where on the graphing paper the 2 lines cross each other. Now, you're not going to, at home, you're not going to be able to, if you don't have graph paper, right, you're not going to be able to follow that instruction. But nevertheless, for me, draw an obtuse triangle. That should be easy, right? Just a triangle. Obtuse means it's got an angle bigger than 90 degrees in it, right? Let's see. It may also help if you, I should have said this earlier, but this is not necessarily any obtuse triangle will do. It may also help if you draw the triangle so that one side of the triangle is horizontal. One side of the triangle is horizontal. Okay. So you may have done that already, but it, okay, I'm just going to go around and look at what people drew. So for you people on Zoom, I'm going to step out of the frame here for a moment, but I just want to see what people. Anyhow. Yeah. Which one? Okay, I will want to get that. Okay, so I forgot these. Okay, someone want to share their obtuse triangle with me? Chrisio, what's your answers? So I'm not going to show it on the. Not going to show it on the camera there, but there's Mauricio's triangle. That looks obtuse, right? Because obviously this angle has to be more than 90 degrees, right? Okay, so that one's very good, right? Let me try to recreate this one on the screen, Mauricio. Then I'll give you your paper back because we're gonna use this triangle in just a second. So hang on to the one you've got, right? Okay, because we're going to do something like that in just a moment. So I'm lowering the screen for you guys at home. Let me not close my notes there, and let me see if I can redraw Mauricio's triangle here. If I can count the grid points right. Okay, so it looks like you've got the base, which is the horizontal side of that triangle. I'm going to call that the base. Looks like that one is 1, 2, 3, 4, 5, 6, 7, 8 units. So let me make a base here of 8 units. So we'll use this point as one of the vertex points. 1, 2, 3, 4, 5, 6, 7, 8. So there's where he's got one of his other vertex points. And then it looks like, let's see there. It looks like his other point, 1, 2, 3, 6 is 6 over, and let me count it here. 2, 6, 7 up. Right there, I think, is the other vertex of Mauricio's triangle. Okay, so let me see if I can connect these with straight lines. That's not easy to do when you're looking down. So I didn't make that line too straight, right? Y'all just squint and pretend this is a straight line. Okay, and sort of triangle. Okay. The reason that I wanted you to draw that triangle is we're going to learn a little formula here that might be useful to us, and that's a formula for computing the area of triangles. Okay, so the area inside of the triangle. So we have to work with triangles a lot, and sometimes it'll be useful for us to be able to compute areas. Okay, so the area enclosed enclosed there by the triangle. All right, so let me show you how to do that here. Okay, but to do that, I'm going to show you another formula that also is useful to us, but we're going to use this formula a little bit less than the area of the triangle formula. All right, so if you have a parallelogram, okay, then you can compute the area of the parallelogram very easily. Okay, there's a very easy formula for doing that. Okay, and that formula is just what you see there. Okay, the area of a parallelogram, is its base times its height. All right, now you know this formula very well. Okay, because you compute areas of you know how to compute areas of certain parallelograms very easily. Okay, for instance, a rectangle. Here's a rectangle, right? A rectangle is a type of parallelogram, right? Okay, so this formula applies to rectangles, but it also applies to other parallelograms as well. Now, let me explain to you what I mean by the base of a parallelogram and the height of a parallelogram. Okay, so if you take a parallelogram and you position it so that one side is horizontal, okay, the length of that side is going to be called the base of the parallelogram. So in this rectangle, what I've done is I've drawn it so that this side is horizontal, right? Okay, so that becomes the base of the parallelogram. And then the distance from the base up to the shortest distance, I should say, okay, from the base up to its parallel side. Okay, remember this is a parallelogram, right? So it's got parallel sides, correct? So the distance from the base up to its parallel side is called the height of the parallelogram. That makes sense, right? Okay, so here's my rectangle, right? Okay, so it's been drawn here, right? And so if you measure the distance from the base there up to, there's the parallel side, that's called the height of the parallelogram. Well, in a rectangle, the height of the parallelogram is obvious, right? Okay, because the height is just going to be the length of the vertical side in a rectangle, correct? Okay, so and of course, how do you calculate the area of a rectangle? Yeah, it's length times width, right? Or in this picture, that would be what? Base times height, right? Okay, that would be base times height. So for a rectangle, this formula is very obvious, right? Okay, but a rectangle is a parallelogram. But the cool thing is this same formula that you use for computing areas of rectangles, that applies to parallelograms in general. Okay, so it's not just a formula for rectangles. This formula works for all parallelograms. All right, so here I've drawn a parallelogram that's not a rectangle, okay, and I've drawn it so that one side is horizontal, okay, so that's going to be my base. And now the height here in this parallelogram, the height is not going to be one of the sides of the parallelogram. But the height is, as I described it, it's the distance from the base up to the parallel side to the base, right? Okay, so here is the height in this parallelogram. Okay, it's not the length of this side, right? It's this vertical distance, right, from the base up to its parallel side. That's the height. And if you just take the base times the height, that's going to be, believe it or not, that's the area of the parallelogram. So that formula works for all parallelograms, not just for rectangles. Okay. So that's very nice. That's a very easy formula to remember, right? Because you already know that formula, okay, very well, right? You know how to calculate the area of rectangles since, when did you learn to do that? Second grade, maybe? I don't know, third grade, okay? Probably when you learn multiplication. So that's an important application of multiplication, right? So, well, there it is, okay? Now, it turns out then that you can use this fact, okay, that the area of parallelograms is computed this way. You can use that fact to derive the formula for the area of a triangle, okay? And it turns out the area of a triangle is just 1/2 the base times the height. Well, let's look at this obtuse triangle now, okay? So again, I drew it so that one side was horizontal. That obviously is the base, right? Okay, that obviously is the base. Now look, we don't have a parallel side to the base, correct, right? In this triangle, we don't have a parallel side to the base. So what is the height here? Well, the height here is obviously this distance, right? So it's the distance from that vertex on top, right, down to the horizontal side. Okay, if you extended the horizontal side here to the left there, right? Okay, so you can sort of think of the horizontal side as sitting on the ground, and then the height of the triangle would be, you know, what you would intuitively call the height of the triangle, right? The distance from the top vertex of the triangle, right, down to the quote unquote ground. That's the height, right? So here's my base, and here's my height. All right, so and then take that 5 to 1/2 of that, and that is the area of that's the area of the triangle. Can you compute the area of the triangle that you drew, okay, for me? All right. So see if you can compute the area of that triangle. And that's why I told you to put the vertices of the triangle at grid points, okay? Because that makes it easier to find the base and to find the height. All right. So if you want to, you know, you can turn your paper around, right? So that one side is horizontal, so you'll know what the base is. You need to. And then that makes it easy to compute the height too. Okay. $24. Yeah. Oh, okay. Here. Oh yeah. So there's your height. That's 2. There's But you get the idea of okay. All right. So yeah, so y'all can easily. What's this one? The base here was I was calling that off, right? So what? 1, 2, 3, 4, 5, 6, 7, 8. That's supposed to be 8, and the height there, I think was I forgot 7. So just 8 times 7 there, divided by 2. So that's 28. Okay. So the area of this shaded area there is 28. Remember now when you're measuring area, it's in square and then whatever unit of measure using, right? So here I'm just going to say square units because I don't really know what these to measure are, right? Okay. All right. So it's easy, right? Can you see why this formula is correct? Let me sort of demonstrate it for you. It's easy to take this triangle, this obtuse triangle, it's easy to take it and create a parallelogram out of it, okay? Here's what you can do. Start here at this vertex and draw a line across, okay? Make it horizontal because I want this line to be parallel to the base, all right? And I'm gonna make it the same length as the base. So what was my base there? 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to draw it across to here. All right. And then I'm going to connect this point down to the end of the base there. And when you do that, notice you get a parallelogram, right? Okay. So, and that triangle is exactly half of that parallelogram, right? The original triangle I drew was exactly half of the parallelogram. But we know what the area of the parallelogram, right? If this formula is correct, right? It's this base times this height, right? Okay. And then the triangle that I was interested in was half of that, right? Half of that area. So that's where the that's where that formula for triangles comes from. By the way, I did draw there. There are some pictures of the other 2 types of triangles, right? So again, obtuse has a bigger than a 90-degree angle in it. A right triangle, which is what we were really most interested in, has one angle that's exactly 90 degrees, right? And then an acute triangle like this one, all of the angles are less than 90 degrees. Okay, so if you just hear me throw out these terms, you'll know what I'm talking about. But most frequently, we're going to be interested in right triangles. Okay, well, there's our little tour of some facts from geometry. Okay, they're kind of just random facts from geometry, sort of, that are going to be useful to us in the class. Okay, and now what we're going to do though is we're going to I'm going to show you how we can combine ideas from geometry with ideas from algebra. You know how to do this already, so I'm reviewing, okay, all right? But so this is just kind of a reminder of how we're going to combine geometry, coordinate geometry, 2-dimensional geometry with algebra. Now, this is extremely important in calculus because many of the concepts from calculus, or many of the questions that calculus attempts to answer, are very geometric questions. Okay, there are questions that they're really very ancient questions, actually. Okay, when geometry was much more important in mathematics than algebra was. Okay, But the tools that we're going to use to answer these geometric questions are going to be algebraic tools, all right, in calculus. The tools that you use to answer the geometric calculus questions are algebraic tools. So we have to learn how to kind of combine or marry our geometric knowledge with our algebraic knowledge. And I'm going to show you how that's done, or one way that's done, or the classical way that that's done now. But you're already familiar with this, so this is going to feel like just like a review to you, I hope. But if it doesn't, then that's okay too. All right. Okay, so here's where we start. I mean, this is where this is where this idea of putting geometry and algebra together always begins. Okay, and suppose now that we have this equation, 2x minus y equals 3. Okay, so that's obviously an equation because it has an equal mark in it, and it has two unknowns in it. Okay, now of course, you know, when we have equations with unknowns in them, right? You know, our first instinct is to solve the equation, right? That is, find the values for the unknowns that will make the equation true when you substitute those values for the unknowns, right? That's what we mean by solving the equation. Remember last time we solved an equation in class when we were working on that problem about finding that point on the x-axis, right? Remember? And we solved this equation. And it took us a few steps, right? But we solved this equation to find that value for the unknown x, right? That would make that equation true when we substituted for x. And it turned out to be the correct value for x was, right? We didn't actually check that though, so maybe we should have checked that, but I'm not going to check it now. When we substitute 4 for x into this equation, we'll make the equation true. Both sides of the equation will turn out to be to one another, right? Now, in this equation, notice though, even though it's kind of a complicated equation, it's simple in one sense. It only has one unknown in it. All right, okay. But we just had one unknown in this equation. But in this equation, which is a heck of a lot easier in terms of, you know, the expressions in the equation, right? The operations in the equation are much simpler. But this equation is a lot more complicated because it has two unknowns, all right, instead of just one, all right? And that makes the equation, in some sense, infinitely harder to solve, all right? Even though we only went from one unknown to two unknowns, from just x, now we have x and y. This kind of multiplies the complexity of the equation by an infinite factor. All right, let me show you what I mean. Okay, now what doesn't change though when you have two unknowns in the equation is what it means to solve the equation. To solve the equation means you find values for the unknowns that you can substitute, right? That will make the equation true. All right, so we want to find now values for x and y so that when we substitute for x and y, we'll make the equation true. This is a pretty simple equation, so you might be able to find some solutions just by inspection. I mean, just by looking at the equation and kind of not really guessing, but just looking at the equation and just in your mind, you know, you can come up with solutions. Can someone come up with solutions for this equation for me? Just one will do. What now? 2 for x and 1 for y. So let me put this in this table here. All right. Okay. And Robbie, I'm going to put your proposed solution in the table. And of course, it's very easy to check that, right? And you are doing that mentally, so it's really easy to check it. Because, you know, 2 times 2 minus 1, well, that's 4 minus 1 is equal to 3, right? So that obviously makes the equation true, right? Okay. So notice that our solutions here now are pairs of numbers, because you have to have a solution for x and a solution for y, right? Okay. So when you write down a solution, it's not just x equal something. You have to write something for x and something simultaneously for y. Okay. All right. Now, you know, in some sense, we've solved the problem, right? We did solve the equation because we wrote down a solution to the equation. But typically in math, when you say solve an equation, that means you want to write down all of the solutions to the equation, okay? Because some of the solutions might be more interesting to you than others. So, so when we say solve, we mean usually, unless you're told, one solution is enough. Usually, when the instruction is solve an equation, you want to write down all the solutions. So, is 2 and 1, is that it, or did someone come up with a different solution? Someone on Zoom there, can you propose another solution for me that we can add into our table other than x equal 2 and y equal 1? So here's I can't see your name. Let me move that. Is that I thought it was Azel from the little part of the picture I could see. So Azel says x equals 3 and also y equals 3. Okay, and Azel, yeah, that's great, right? Because that's going to be 2 times 3 minus 3, and that certainly is equal to 3, right? Okay, so there's another solution to the equation. Does anybody have another one? 5 and 7. So 2 times 5 there minus 7. Yep, that is indeed. That's 3, right? So so there's another solution to the equation. And at this point here, we kind of get kind of a sinking feeling, right? Okay, because it's kind of easy to find solutions, and so we get this uncomfortable feeling that, whoops, there's going to be a lot of solutions to this equation, right? So if I'm trying to write down all of the solutions, that's going to be a problem, okay? Because it already looks like there's a lot of them. All right. So how can I sort of accurately answer this question? How can I sort of accurately solve the equation when it looks like, wow, I'm going to have lots of solutions here, right? This seems like it's kind of an unreasonable instruction, right? Solve that equation because it looks like I'm going to have lots of solutions. In fact, I'm going to get infinitely many solutions here, folks, okay? You're going to get infinitely many solutions. That's why I said this equation, even though it looks easier than that equation from the first set of notes, it's in some sense, it's infinitely more complicated because it's going to have infinitely, instead of one solution, it's going to have infinitely many solutions to it, okay? And in fact, how can I easily, so y'all have done this enough, how can I, in prior classes, I know, how can I easily just generate solutions to this equation? Sort of methodically, how can I just create new solutions to this equation? Well, okay, no, what process though can I go through just to sort of automatically generate solutions to this equation? Robbie, what do you want to say? Oh, I see. So what Robbie's suggestion here is just plug in something for x and find what the matching y is supposed to be, okay? Or you can also do that vice versa. Plug in something for y, right? Just plug in a number for y and then figure out what the matching x has to be, okay? And you can just keep doing that for as long as you like. Let's try that just a little bit. So I'm going to start by plugging 0 in for x because that's so easy to do arithmetic with, right? Okay, so I'm going to plug 0 in for x, but I could have plugged any other number in for x. And when you plug 0 in for x, what happens? You get 2 times 0 minus y is equal to 3, right? And so that's the equation. Minus y is equal to 3, and that's very easy to solve for y, right? In fact, what's y equal to there? Minus 3, sure, right? Okay, so there's another solution to the equation. Or you can do this vice versa. Plug 0 in for y, okay, and you get 2 times x minus 0 is equal to 3. Or 2x is equal to 3, which means x is 3/2. Now, 3/2 is a perfectly good number just because it's a fraction, right? So don't let the fact that it's a fraction scare you off, right? So there's another solution to the equation, or you can keep doing this, okay? Let's put in let's put in a negative number for x here. I don't have any negative values for x there. So if you plug -2 in for x, you get 2 times a -2 minus y is equal to 3. So let's see, that's -4 minus y is equal to 3. That looks like minus y is equal to 7, because I'm going to add 4 to both sides of the equation. So I'll get minus y is equal to 7. And if minus y is equal to 7, then what's positive y equal to? What now? If minus y is equal to 7. -7? So there's another solution to the equation. Wow. Okay. So if you get this problem on a test, you see, and you were supposed to write down all the solutions to the equation, that problem would take you the whole test, right? Plus the rest of infinity, because there are infinitely many solutions to that equation. So this is not a reasonable way of expressing the solutions to this equation, right? Because there are too many of them. All right, there are too many of them. All right, so here is where Descartes again was helpful. Okay, what Descartes said is, so remember, Descartes is the mathematician whose name is associated with our two-dimensional coordinate system, right? Our rectangular coordinate system is called the Cartesian coordinate system. Okay, because Descartes is credited with inventing that, although probably that's not really Descartes. Okay, and Descartes is also credited with this idea, right? Which is Descartes says, you know, you can't write down all the solutions to this equation. Okay, so Descartes says, I will do the next best thing. I'm going to draw a picture of these solutions. Okay, I'm going to draw a picture of the solutions to this equation. Okay, now how does Descartes draw a picture? So this is really important point. Okay, so it's very simple-minded, but it's a really crucial point. Just because it's a simple point doesn't mean it's not an important point. Okay, all right. See, this is the question that Descartes wanted to answer. How do I draw a picture of the solutions to this equation? So what Descartes said is, these solutions look like coordinates of points, right? Okay, because I have an x solution and I have a y solution. So I can think of these solutions as coordinates to points. And of course, once you've got coordinates to points, what can you do? Plot them, right? Okay, you can plot them, sure. All right, so that's exactly what Descartes suggested doing there, right? Is to plot these solutions. So let's see if we can plot them. I want to do it kind of carefully here. So x2 and y1, don't let me make a mistake there. All right, so there's one. 3 and 3 there. Okay, and 5 and 7 up here, right? And 0 and -3 down here. Okay, and 3/2 and 0 is right there. And then -2 and -7, -2. And what do you notice about those points? They're all on a straight line, right? Okay, they're all on a straight line, right? So you don't just get some random points there scattered on your two-dimensional coordinate system when you plot the solutions to that equation. All of those points end up falling on a straight line. How convenient can that be, right? Okay, so that was very exciting to Descartes. All right, mainly because, you know, lines are a very basic geometric figure, and lines have been studied very extensively as a geometric figure hundreds and thousands of years by the time of Descartes, right? Okay, so a lot was known about straight lines, right? And so Descartes knew a lot about straight lines. So see, he could use his knowledge of straight lines here once he realized that solutions to that equation all fall on a straight line. Okay, so that's not just coincidence in this case, right? Indeed, all of the solutions to this equation all of the solutions to this equation are going to fall on this line that's drawn here. Vice versa is also true. If you pick any point off of this line, okay, so if you can pick some point off of this line and you plug its coordinates into this equation, there are going to be solutions to the equation. All right, so there's an actual a total correspondence between the solutions to this equation and the points on this straight line. Okay, every solution to the equation is a point on this line, and every point on that line is going to be a solution to that equation as well. Okay, so in a sense, that line is the solutions to that equation. Okay, that's it. We've drawn a picture of all of the solutions to this equation. See how that elegant that is, right? So, so when you're asked to solve this equation by drawing this picture, you have an effect solve that equation. Okay, you've drawn a picture of all of the solutions, all infinitely many solutions to that equation. Okay. All right. So again, see, now we have this marriage now, right, between algebra, because solving equations is an algebraic type of problem with geometry, right? Because graphing lines is a geometric sort of problem. Okay. All right. So this picture that we drew here of the solutions to this equation, this is called the graph of the equation. All right. Okay. So we don't call it a picture of the equation. We call it a graph of the equation. And what we mean is we plotted on that graph there, right? On that picture, all of the solutions to this equation. Now, we are going to go on and learn more about equations whose graphs, right? And in other words, equations whose pictures of their solutions turn out to be straight line. These are called linear equations. And we're going to talk about those extensively, all right? And we're going to actually learn why the graphs of solutions to equations like this one turn out to be straight lines, and also why, if you have a straight line, you can write down an equation like this whose solutions are the same as the straight line. Okay. Now let's look though at a let's look now though at an equation that's a little bit more complicated than a straight line. Okay. So here's my instruction. Now I want to graph this equation. Okay. So when I say graph the equation, what does that mean? That means draw a picture of what? The solutions to the equation, right? I want to draw a picture of the solutions to the equation. So this is an equation now with two unknowns in it. All right. It's got two unknowns in it. So this equation is going to have infinitely many solutions. Okay. So when you have equations with multiple unknowns, you end up with infinitely many solutions. Okay. So I cannot write down in a table, I cannot write down all of the solutions to this equation because there are too many of them. Okay. But I'm going to do the next best thing. Instead, I'm going to draw a picture. Right now, to draw the picture, we're going to have to create some solutions, right? Okay. So we'll have no hope of drawing this picture if we don't create some solutions to the equation, right? Okay. Notice this equation is a little bit more complicated, not because it has more unknowns than my first example, but notice that just the expression here is a little more complicated, right? Here I have x squared instead of x, like I had in the first example, and here I have y squared instead of y, like I had in the first example. All right, guys, now here's what you have to do. You're going to have to help me generate some solutions here, okay? Because so otherwise, we're not going to know where to start, okay? So so how can y'all help me generate some solutions? This one's a little bit harder to generate solutions just by inspection. Just from looking at the equation, it's harder to generate solutions. A calculator might be helpful, by the way. So, all right. So let's try generating some solutions. Where would y'all start? Remember the trick we had for creating solutions in the first example? What did we do? Well, when you said 0, be a little bit more. So we plugged in something for x, right? And then when we plug in something for x, notice that's going to give you an equation with just one unknown in it, because the x will be missing then. And then hopefully you can solve that equation, right? So I'm going to plug in something for x and then solve for y, right? To get a solution. And I can do vice versa as well. I can plug in something for y and solve for x as well to create some solutions. Now, Jad, though, you were specific. What number did you want to plug in for x? 0, only because that makes the arithmetic easy. Okay, all right. So let's try Jad's suggestion there. I'm going to plug 0 in for x. So I have 0 squared plus y squared is equal to 25. So that's so easy. That's y squared is equal to 25. So if y squared is equal to 20, that means what? Y must be what? The square root of 25, right? Which is 5. Yeah. Okay. Now, however, be careful. The number 25 has 2 square roots. The number 25 has 2 square roots. One of them is positive 5, but negative 5 is also square root of 25. So to indicate that, I'm going to put plus or minus in front of the square root sign or the radical sign here. And so you have plus or minus 5. So notice here you get 2 when you plug in 0 for x, you get 2 entries in your table. 0 and 5 is the solution, and 0 and minus 5 is a solution, right? So that's nice. That's kind of a 2 for 1 there. Okay. We can play this game backwards too by plugging 0 in for y, and you're going to get, when you plug 0 in for y, notice you get x squared is equal to 25, which means, of course, x is what? Plus or minus 5. So you get 2 more solutions there. Let's go ahead and, we're not through creating solutions yet, but let's plot these just to see where we're, just to sort of get a feeling for what sort of picture we might be looking at. And it's a little bit scary when you plot these. So x0, y is 5. Let me do this right. So x0, y is 5 is up there. x0, y equals minus 5. 1, 2, 4, 5 down here. x5, y0 over here. And over here also. Oh, darn. Okay. So that's a little bit confusing, right? It's not a straight line for sure, right? Okay. So this graph is going to be more complicated. Hopefully, it will turn out to be something that's nice and symmetric. Hopefully, we won't have some weird curve that's just going all over the place, right? Because if that's the case, then I'm not going to have much luck doing this by hand. All right. What do y'all suggest now at this point? You want to try some more? Create some more solutions, Emil? And Emil, you happen to say, oh, 3 and 4 happen to be solutions. Okay. Oh, that's good. So you just saw that by inspection. So 3 squared plus 4 squared. Oh yeah, that's 25. Emil, you actually get lots of solutions with 3 and 4. Because won't 3 and minus 4 work? What if see what I'm saying here? If x is 3, can't y also be minus 4? Because 3 squared plus minus 4. Yeah, right. Okay. And What about minus 3 and 4? That will work, right? And what about minus 3 and minus 4? That will also work. Okay, right? Yeah, right. So let's try plotting those now. So 3 and 4 up here, 3 and minus 4 down here, minus 3 and positive 4 up there, and minus 3 and minus 4 down here. Oh, now that's looking nicer. Okay. Any suggestions there, maybe? A circle, yeah, that's what I would think too, right? It looks like it might be on a circle. Let's try something else here. Something where we have to do a little bit of extra work there. So let's try x to be, how about x to be 1? Y'all want to try x being 1 or x being 2 to see what happens? Because then I'll have a point, you know, at x equal 1 and x equal 2. Let's see what happens in that case. So which one do y'all want to pick there? 1 or 2? 2? Okay. So now we have to do a little bit of arithmetic. So let's set x be 2. So I'm going to plug that into my equation. So I have 2 squared plus y squared is equal to 25. So that means 4 plus y squared is equal to 25, or y squared is equal to 21 if you subtract 4 from both sides, right? And that means then that y is going to be plus or minus the square root of 21. And now we need your calculator because 21 is not a perfect square. So what's the square root of 21? A couple of 1 decimal place is probably enough because we really can't plot 2 decimal places very well. What is it? What? 4.6. Let me get rid of this. I can get rid of some magnification. So plus or minus 4.6. Okay, so let's see how that fits into our picture here. So when x is 2, y is either 4.6 or minus 4.6. I'm running out of table room here. So 2 and 4.6. 1, 2, 3, 4.6, maybe right there. And minus 2 and minus 4.6, maybe about there. And Emil, you could also use x equal minus 2. And the arithmetic would almost be the same because minus 2 squared is also positive 4, right? So that means that you would have minus 2 and 4.6 up here and minus 2 and minus 4.6. Where's that down here? Right about there. Wow, now that really does look like that's going to be a circle. So I'm thinking, yeah, that's got to be, must be corrected, right? That's thinking circle. We're not 100% sure of that, but sure looks like that, right? And that is in fact correct. Okay. Graph of this equation is a graph of that equation is a circle. It's a nice familiar geometric figure, just a circle. Radius is 5. The radius of this circle is 5. That's the distance from the center out to the edge of the circle. And the center of this circle is right here at 0, 0, right there at the origin. Okay. Now, well, I think this kind of illustrates the issue that you're going to run into when you're graphing equations, and that is when you graph just an arbitrary equation, the graph can come out to be almost any sort of figure, all right? Okay, so you really need to have some prior knowledge. You really need to have some prior knowledge of what to expect when you graph an equation, draw the solutions to an equation. Okay, so that's one of the things that we're going to learn here in this course, and that you will study a lot more in calculus is if you're given an equation with two unknowns and you want to graph the solutions, what should you expect to see when you draw that graph? Okay, what sort of geometric figure are you expecting to see? That makes it much easier to actually construct a graph. Okay, yes. Oh, I see. So if you try here, x equals 10, all right. So which would be something that you might try, correct? So because who knows, right? I mean, why not just x equals 10? So let's see what happens when we do that. We get 10 squared plus y squared is equal to 25, or 100, right? Plus y squared is equal to 25. So subtract 100 from both sides and you get y squared is equal minus 75. And you automatically say, oh, that has no solutions. Because when I square y, it cannot be negative, right? Okay. No matter what I substitute for y, if I square it, it's not going to turn out to be negative. So this equation doesn't have any solutions. So that tells you you don't have any points here on this graph with the x coordinate of 10. Okay, all right, yeah, all right, because there are no solutions to this equation where x is 10. All right, okay, so so that can happen. All right, that won't happen with straight line, but it could happen with other types of equations that we're graphing. All right, so now I'm gonna key you in here to what equations for circles look like. Okay, and then we'll take our break. So let me show you. All right, so here's what the equations for circles look like always. And so if you see an equation that fits this form, okay, then you know when you graph it, you're going to get a circle. Okay, so if you run across an equation that fits this particular format, then you automatically know, oh, that graph's going to be a circle. So it's easier for you to graph. All right. So so if you have a circle that's center is at this point, doesn't have to be the origin. At this point, x equal h, y equal k. So these can be any two numbers, right? The center is at this point, and you have a radius of r. Of course, the radius has to be positive, because if you have a circle with radius 0, then don't have a circle, right? Okay. But radius r. Here's what the equation for that circle looks like. Okay. Has this format. So you have x minus, notice that's the x coordinate of the center squared, plus y minus the y coordinate of the center squared is equal to the radius squared. This is called the factored form or the standard form for the equation of a circle. So x minus x coordinate of the, so this is a number, x coordinate of the center squared, plus y minus, this is a number, right? Y coordinate of the center squared equal to, this is a number, r squared. The unknowns here are x and y. H, k, and r are not unknowns, all right? Those are numbers that will vary depending on the circle that you're working with, right? Now, let's see, does that, what I just wrote down here, does that fit this circle that we just graphed? Well, what was the center of this circle? You can see it there, what? 0, 0, right, the origin, and the radius is what there? 5. So according to that standard form, the equation for this circle should have been x minus the x coordinate of the center squared plus y minus the y coordinate of the center squared is equal to the radius squared. Is that what we had here? Is that equation? Yeah, because x minus 0 is just x, right? So that's x squared. Y minus 0 is just y, so that's y squared equal 5 squared is 25. Yeah, there it is. Okay, so indeed that that equation fits perfectly into this so-called standard form or factored form for the equation of circle. All right, let's stop there then and take a break. Okay, so we'll take a break here till about say 20 after 11, and then we're going to come back and practice with this standard form for the equation for a circle. So in a sense, you're going to know everything there is to know about circles. Okay, all right, at least as they look in algebra. Notice we only had one example of a straight line and we kind of skipped over that. Don't worry, we're going to come back to lines. Lines are simpler geometric figures than circles are. We're going to come back to lines. We're going to spend a lot more time with lines than we do with circles. All right, but we're kind of going out of order here. We're going to start with circles first. Okay, all right, so let's take our break and let me stop the recording here and then we'll come back and keep going. All right, so for you guys online, I've restarted the recording. All right, so we are back in business here. And first things first, so let me pass the roll sheet around, right? So sign where you signed last time. But if you were on Zoom last time, right with the name. And make sure that gets all the way around. Okay, so there's the standard form or the factored form, also called, for the equation for a circle. So let's practice with this sum, and we'll start off with just an easy one. Suppose we want to graph this equation. All right, so just immediately recognize there that that is the factored form, right, for the equation of a circle, right? So that makes it easy to graph the solutions, draw a picture, right, of the solutions of this equation. Okay, so you don't have to really create a table of points to draw the graph here. All right, you're going to be able to graph this one by hand without difficulty. If you can recognize what the center is, right? So what would be the center of that circle? Yeah, so what's the x coordinate of the center? 2. It's going to be positive 2. So that you have to kind of watch for carefully. Notice that in the factored form for the circle, it says x minus a number, and so here you have x minus 2, so the number that you're subtracting is 2. All right, so the center for the circle is at x equals 2. Now notice that here in the second set of parentheses, right, you have y plus 1, right, but y plus 1 is the same as y minus a minus 1. Okay, right, and so that means then that the y coordinate for the center is negative, right? So remember, when you're writing a circle in standard form, you must always have x minus a number, y minus a number. All right, so there's our center at 2 and minus 1. So that's not part of the circle. That's just the center of the circle, but the actual edge of the circle, right, is some radius away from the center, correct? And the radius here would be, what would the radius here be? Well, 36 is 6 squared, right? So the radius there is going to be 6. Notice that in your standard form for the equation of the circle, right, it's on this right hand side here, you have radius squared. So since 36 is 6 squared, you know the radius is going to be 6. So now it's easy to generate points, right, on the actual edge of the circle, because just starting from the center, just go a distance 6, right, from that center. So it's easy to go horizontally and vertically a distance 6 from the center. If you want to go some other direction, that's a little bit trickier. But so this point would be on the circle, right? 1, 2, 3, 4, 5, 6 away from the center, up 6. 1, 2, 3, 4, 5, 6, right? Is that here? Yeah, okay. And then down 6. 1, 2, 4, 5, 6, right? And then over 6. 1, 2, 3, 4, 5, 6. Did I do something wrong? And so we have at least those, we know at least those 4 points are on the circle. And that's really should be enough to allow you to draw a fairly decent circle. Depends on how steady your hand is. I probably will do a terrible job here of trying to connect these points with a circle. No, could have been worse. Okay, so there. So everyone got to sign it there. Who's here? All right. So there is the approximately there that that circle that corresponds to that equation. So again, it's important to remember, right, that if you were able to write down all of the solutions to this equation, right, and plot them, you would get points on this circle. Vice versa, if you pick a point out of this circle, right, if you're able to locate a point on this circle and you plug its coordinates in for x and y in this equation, they will satisfy the equation. The equation will be true. Okay, so there's a one-to-one correspondence there between the solutions to the equation and the points on the circle. All right. Okay, let's let y'all try one now with your graph paper. Okay, so see if you can graph this equation. So see, that would be a formidable problem if I just gave you that equation and said, oh, graph the solutions to that equation for me, and you know, you didn't have any idea what to expect, right? That would be tough to do. Try to generate solutions to that equation, right, and connect them with a nice curve. But now with your pre-existing knowledge, right, this is going to be easy for you, right? All right, so everyone try graphing this one. You guys at home also, all right? Try graphing that one for me, and then we'll watch you, and then we'll talk about what the graph looks like. You're not Riley, you're Fernando. This is right, yeah. Okay, so I think most people got pretty far along there. So someone at home on Zoom, can you tell me what the coordinates of the center were going to be for this circle? So Kenneth says -2 and 2. Is that right? Is that what other people got there? Okay, -2 and 2. Hannah, you said 3 and 1. Is that for this question? Hannah, are you there? Or is that a previous question? Can you turn your, does your mic work, Hannah? I just wanted to ask you why you were thinking 3 and 1. Okay, so I think it is -2 and 2, right? What is the radius then? So Hannah, did you get the radius? Well, Kenneth beat you to it there, right? But Hannah, you also said 3, right? So that's perfect, right? Okay, yeah. So the radius there is going to be 3 because 9 is 3. 9 there is 3 squared. So once you know and then once you know the center and the radius, right, then it's pretty easy to draw at least a fairly decent version of that circle, right? So there's the center. The radius is 3. So if we move away from the radius 3 units, that gives us points on the circle. It's easy to figure out what 3 units are if you go horizontally and vertically, right? Okay. So these must be other points on the circle. And so our circle, something like this. Nice. Okay, is that what y'all drew? I think that's what everyone, drew there. Is that what y'all drew at home? Something like that? Okay. Does that look right? All right, so wow, see, that's already powerful knowledge there, right? Being able to graph the solutions to a complicated equation like that one without much work at all, right? We didn't have to generate any solutions, right? Okay, only had to plot a few points, and we got a really pretty nice graph there of that equation. So remember that graphing that equation is kind of the same as, right, writing the solutions to this equation, right? When you graph that equation, you have in some sense solved this equation, right? You've drawn a picture of all of the solutions to this equation. Now, sometimes, however, we're going to go in the opposite direction. All right. So here's the same question, except when I say it's in the opposite direction, Here we are given the circle. So we're given the circle. We're not actually shown the circle, but we're given a verbal description of it. So you can visualize the circle very easily, or you could actually draw the circle if you wanted to from this description. So here you're given the geometric object first and the circle, and now you want to write down the algebraic version of the circle. In other words, the equation for the circle. So suppose you had a circle there, and the radius is 3 and the center is at 2 and -5. So I didn't draw a picture of that. Okay, but you can imagine that. And we want to write down the equation for that circle. What's the equation whose solutions correspond to that circle? Okay, so can y'all write that down? Well, let me do it, and then I'll give y'all a practice problem here. Okay, all right. So remember, we're gonna write the equation down in standard form. That's the easy way to write down the equation. And remember, in standard form, that means what? You take x minus the x coordinate of the center and you square that, right? So what's the x coordinate of the center here? 2 plus, and then you take y minus the y coordinate of the center, which in this case is -5. So you get a double negative there, right? Square, don't forget to square that, is equal to the radius squared. Just that simple, right? So easy. So you have x minus 2 squared plus y plus 5 squared is equal to 9. So now, unless you're asked to simplify the equation, you can just leave it in this factored form, this standard form. Simplify means, remember, as we discussed last time, that means carry out the arithmetic in the equation by hand. But unless you're asked to do that, there's no reason to simplify the equation. So you can leave it just in this so-called factored form. All right, so here's the one that I was going to have y'all do. All right, okay. So you guys do this for me. Write the equation for this circle. You can imagine what this circle looks like, right? It's got radius 10, and the center is there on the x-axis, actually, at -7 and 0. All right. So center at -7 and 0, radius of 10. So that's a pretty big circle because it's got a radius of 10. So write down the equation for that circle, and you don't have to simplify. Okay. At least that's not in instructions. All right. So at home too, also try that. Write down the equation for that circle that is verbally described there. That make it hard. Okay, now y'all are passing. That's pretty simple. Say the question like this on the test, and y'all are gonna kill that one. Easy, right? So we have just x minus a minus 7 squared, right? X minus the x coordinate center plus y minus 0 squared is equal to the radius squared. And you can make this look a little bit prettier without simplifying it completely, because x minus a minus 7 is x plus 7. So you can write x plus 7 squared plus, and since y minus 0 is just y, you can just write y squared, okay? Is equal to, and if you want to square the 10, that right 100, but you can leave that also as 10 squared. Now, yeah, that's not really for this one because there's not much work to do there, right? Okay. Now I'm good, but now you're not asked to do this in the problem, but I'm going to go ahead and simplify here. Okay, so to simplify means again carry out arithmetic you can by hand. All right, so the only arithmetic you can really do here is square x plus 7. All right, so remember we discussed this last time. Some people had forgotten how to square things like x plus 7. Remember, that means you multiply it by itself, right? So x plus 7 squared is x plus 7 times x plus 7, which is x squared plus 7x plus another 7x plus 49 plus y squared is equal to 100. And so this is x squared plus 14x plus y squared. And I'm going to take the 49 and move it to the right-hand side with the 100. So I get 100 minus 49, which is 51. Okay. So there's kind of a simplified version of that equation. X squared plus 14x plus y squared is equal to 51. The only reason I'm showing you that in simplified form is so that it's for a later problem, okay, that we're going to have. Before we get to that, though, let's see if we can do something that's a little bit more elaborate in terms of writing down the equation for a circle. So let's find the equation for the circle that has these points on the circle. So the point 1, 8, and 5 minus 6, those points are not the center, but those are actually on the circle. And they are endpoints. This is important. They're not just on the circle. They are on the circle, but they're not just any 2 points on the circle. They are endpoints of a diameter of circle. So a diameter of a circle means a line that goes from one side of the circle to the other through the center, okay, through the center. If you draw a line that goes from one side of the circle to the other, that's called a chord, but that doesn't necessarily have to go through the center. But if it goes through the center, that's called the diameter of the circle. So here's a picture actually of this situation, right? Okay, so we have this big circle, and it's got this point on it 1, 8, and this point on it 5 minus 6. So those are actual points on the circle, and this line that connects these 2 points is the diameter of this circle. So apparently it goes through the center of the circle, and we want to write down the equation for this circle. All right, we'll write down the equation for that circle. So what do you need to write down the equation for a circle? What 2 pieces of information do you need? Yeah, you need the center and the radius, correct? Right, that's it. That's all that goes into that standard form, right? For the equation of the circle is the center and the radius. So how do we find the center here? That's midpoint formula, right? Because the center has to be the midpoint between these 2 points, correct? Right? That's going to be the center. So, and now you know the midpoint formula very well, right? you find the midpoint of 2 points, right, by averaging the x coordinates, and you average the y coordinates. So my x coordinates here are 1 and 5. So if you take 1 plus 5 and divide that by 2, that's easy. That's going to be 3, right? And what about the y coordinate of the midpoint? You average the y coordinates, right, of your 2 given points. So that would be 8 plus a minus 6, which is really just the same as 8 minus 6 over 2, right? So we end up here with what? 6 over 2, which is 3, and 2 over 2, which is 1. So it looks like the center for that circle is at 3, 1. So you see my picture here is not very good, right? Because the center is really right there at 3, 1. All right, so that's half of the information we need to write down the equation. What's the other thing that I need to know? The radius, right? Okay, so I need to know the radius, and where's the radius in this picture? Sure, it's the distance between the midpoint and one of the points on the circle, right? Okay, so here, for instance, is the radius, right? So we can find that radius, right, by using our distance formula, correct? So do you remember our distance formula? So what do you do there? It has a big square root in it. That's always the easy part to remember. What goes under the square root now? I only need half of this distance, right, Fernando? Right, so not 5 minus 1, but just what? I only need the distance from the center to this point, right? What now? I could do 5 minus 3, or I could also do, since I drew the radius here, I could also do what? 3 minus 1. Yeah, okay. I was looking at the difference between these two x coordinates, but Iris is right. 5 minus 3. So, okay. Square that. Don't forget, plus, and now what goes in the second set of parentheses that we're also squaring? The difference in the y coordinates, right? So is that what? 1 minus 8. 1 minus 8, and square that. Okay. So we end up here with the square root of 2 squared plus a minus 7 squared, right? So that looks like the square root of 4 plus 49, which is square root of 53. Now that sounds like a really awkward radius. That's a little bit more than 7. But it's really, it doesn't matter that 53 is not a perfect square, because remember, when we write down the equation, what are you doing with this anyway? What do you do with the radius in the standard form of the equation? You square it, right? So the square root is going to go away in any case, right? So let's write down now the formula for the circle, right? So it's x minus the x coordinate, right, of the center, which is 3. Square that, plus y minus the y coordinate of the center, right? Square that is equal to the radius squared, right? So that's the square root of 53, but it's going to be squared. So that gives us just 53. So there it is, right? That's the equation for a circle. Wow, we combined really almost all the things we've learned so far in just that one problem. Well, we didn't have any triangles there, or any parallelograms, right? Okay, but a lot of other things we've learned, right, are in that show up in that problem. Okay, now we get to fun part. All right, because when you're given equations for circles or other sorts of geometric figures, they may not always be written in the format that you would like them to be written in. Okay, all right. So let's look at this equation. All right, x squared plus y squared plus 2x minus 6y plus 7 equals 0. And suppose you are asked to graph that equation. That looks terrible, right? Okay, that looks like something that is really going to be difficult to graph. It would be really hard to even just generate solutions to that equation, if even just wanted to, generate points that are on that figure and try to, connect the points, right? It would be even hard to do that. So it'd be hard to make even a table of solutions to that equation. But here's what's going on here. All right, that really is unbeknownst to you to start with. That's really the equation for a circle. It's just written in simplified form. It's not written in factored form. Okay. Remember when we a moment ago when we simplified this equation? Remember we had this circle, and when we simplified, it came out looking like this. Well, that is the same thing that has happened in this problem. We have really the equation for a circle, but it's been written in simplified. Okay. So to figure out what this circle looks like easily, we have to take it and put it back into unsimplified form, put it back into factored. Okay. And that's the process that I'm going to show you now. Okay. Is how to take that equation, which you may not even recognize as being a circle, except you're told that it's the equation for a circle. So we're going to take that equation and we're going to put it back into factored form or standard form so that you can easily see, oh yeah, that's the equation for a circle. And even more, you'll know exactly what the circle looks like, right? Okay, so I'm going to take this equation and put it in this form. That's what I'm proposing to do. All right. Okay, so all right, so there's some steps here. And so watch me carefully, and we may do this a couple of times before I have you do it. All right. So watch me now just at first. Okay. First things I want to do is, if I have any constants in my equation, so that's numbers without variables on them, right? Just constants. You want to get them over on the right-hand side of the equation. So this 7, I want to get it over on the right-hand side. Okay. So let's start with that first. And of course, when you do that, that's going to become -7, right? When you shift the +7 to the right-hand side, that's going to become -7. And at the same time, let's group our variable terms together properly. So the x terms, I want them together, and the y terms, I want them together. All right. So here I have an x squared, but see here I also have a 2x. So I want to get those together. All right. You can't add those because they're not like terms, but I just want to put them side by side. And then same thing for the y term. So I have y squared and then a minus a 6y, right? And then all of that is equal to -7. Okay, that's the first step. So that's just kind of arranging things properly for what we're going to do here. Now, okay, next thing I'm going to do here is I'm going to take my x terms and I'm going to put them in parentheses. So I'm going to group them together inside parentheses. And when you do that, leave yourself a little bit of room here. Okay, so I want to leave myself a little bit of space here inside that parentheses, because I'm getting ready to add something in the parentheses. And do the same thing with the y term. So group them together inside parentheses, and notice I'm leaving myself a little bit of space there after the 6y inside the parentheses. All right, now here's what I'd like to be able to do. Okay, I'm hoping that I can take the x squared and the 2x. I'm hoping I can factor that so that it will look like this: x plus or minus a number squared. Okay. So I want it to. I want to be able to factor these terms that are in the parentheses here, so that when I factor them, I get something that looks like this: x plus or minus a number squared. Now, that doesn't work immediately. Okay. You can factor x squared plus 2x, by the way. You can factor that. Y'all know how to factor this x squared plus 2x? What can you factor? You can factor out what? X. You can factor out x, and you would have x times x plus 2. So this does factor, but it doesn't factor as a perfect square. See, this is not x plus 2 times x plus 2, or this is not x times x. This is x times something different, right? X plus 2. So this is not a perfect square. So this is not what I want, in other words. Now, here's how, though, we're going to make it factor like you want, okay? What I'm going to do is add a number into the parentheses, all right? And in a minute here, I'll show you how you get this number, but I'm just going to tell you here it's 1, okay? But you don't have to guess it, all right? But I just happen to know that it's 1. Now, well, we could try that in a moment, okay? But so I'm going to put 1 there. And what I claim now is you can now factor x squared plus 2x plus 1. Okay, I claim that will factor, and you can't factor out x because x doesn't factor out of 1. But you can factor this as the product of these two parentheses. Now, this is where you're going to have to remember your factoring a bit. Okay, let's see if we can factor x squared plus 2x plus 1. So when you factor x squared plus 2x plus 1, right, something's got to multiply together to give x squared, but that can only be what? Yeah, that's got to be x times x, right? So you know you're going to have an x and an x here. And you also have to have these have to be constants. And when they multiply here, they have to be 1. Well, there's not many ways you can write the number 1 as a product, right? It's got to be what? Times itself, right? Okay. And then you just have to fill in the signs. Remember, you have to fill in the signs correctly so that when you multiply these two parentheses back together, you will get 2x, right? Well, I think the only possibility there is plus, right? We have to put plus in both places. If you put minus in both places, you'd end up with a minus 2x in the middle, and that's not. Let's see, is this correct? X plus 1 times x plus 1, is that x squared plus 2x plus 1? Well, x times x is x squared, right? 1 times 1 is 1, so we got that. What about the middle term? Well, x times 1 is x, and 1 times x is also x. And when you take x and add it to x, of course, you get x. So there you did, there you were able to factor x squared plus 2x plus 1. And how did it factor? It factored as x plus 1 times x plus 1, which is better known as x plus 1 squared. See, I was able to factor this set of parentheses as a perfect square. It was the quantity x plus 1 squared. That's exactly what I need, right, for the equation for the circle. Now, I have to stop here for a moment because I did something here actually illegal. I added the 1 inside the parentheses, right? You can't just add numbers into equation. You know, you can't just make the equation look any way you want, right? Okay. So, because you're changing the equation, right? So if you add 1 here into this set of parentheses, you've got to compensate. You've got to balance the equation by adding 1 on the right-hand side as well. Otherwise, you have changed the equation. So I've got to keep the equation balanced by adding 1 on the right-hand side. So don't forget to do that. Now, I've got to do the same thing with the y squared minus 6y. I've got to add something here so that I can factor the parentheses, but I don't want them just to factor any old way. I want them to factor as a perfect square. The answer is 9. You're right, okay? And but again, I'll show you how you know 9 is the right answer without guessing in a moment. Now, so I claim 9 is it. Don't forget, you added 9 on the left-hand side. So what are you going to have to do on the right-hand side? Compensate by adding 9 as well. Okay. So now let's see how this factors. So let's see, we got to have y times y to get y squared, right? Now there are some possibilities for the 9, because 9 is 1 times 9. So you could put a 1 and a 9 here, but that's not very helpful because that won't be a perfect square. So how else can we get a product of 9? 3 and 3, right? Okay, and that's a lot better. All right. And now what about for the middle sign here? Well, you want to get minus 6y. Not minus and plus, but they're both got to be minus. Oh, but But what you said there is interesting, Emil. If you put -3 and +3, when you multiply back together, look at what happens. You get y times y is y squared. That's fine. And you get -3 times +3, which is already wrong because that's -9, and I have a +9 here. Notice what also happens. Y times +3 is +3y, and -3 times y is -3y. So the y's drop out. So you get y squared -9. But we want y squared -6y plus 9. So this is actually the correct factorization there. And now I claim it factors as what I wrote there. Y -3 times y -3. Which is better known as y -3 squared is equal to, and finally now what do we have on the, what do we have there added up now on the right hand side? Is that 3? But you're done, because that is a circle in standard form. What is the center here? -1 and 3, right? And what's the radius? No. Square root of 3. Right. Okay. Square root. Because remember, in a circular equation, right, you have to have the radius squared on the right hand side. So you have to write that 3 as a number squared. That would have to be square root of 3 squared. Okay. So there's what that circle is. It's a circle with this radius, I'm sorry, with this center and this radius, square root of 3, which is about 1.7 or so. Okay. And so you can easily graph now that circle. Okay, this process that I showed you here of adding these numbers inside the parentheses so that you can factor the result as a perfect square, that's called completing the square. All right, because we're going to complete these parentheses so that when we factor, we can factor those expressions as perfect squares. So notice we had to complete the square twice here in transforming this original equation to a circle equation in standard form. Now, the only mystery here was, how did I figure to add a 1 here and a 9 here? And here's how you answer that. But so you got to remember these steps though. Take the coefficient of the x, not the coefficient of the x squared, that's 1. Take the coefficient of the x, which in this case was 2, divide that by 2. So you always divide by 2. I just took 2 here because the coefficient of the x was 2, and then you square that. So you have 2 over 2, which is 1 squared, which is 1. That's how I knew I had a 1 here. Okay. And same thing here. To add 9, take the -6, that's the coefficient of the y, divide by 2, and square that. So you have -3 squared is +9. So I knew that. When you do that, you're guaranteed that your expressions inside the parentheses will factor. Not only will they factor, they'll factor as perfect squares. Okay, see how many I've got here. All right, let me do this one, and then when we come back on Monday, wow, you're probably already forgotten it all. Okay, well, no, all right, not all right. We're going to stop here. Okay, I'm going to and then when we come back on Monday, I'm going to remind you of this process with this problem. And then our practice immediately will be going to get to try one. Okay. All right. Yourself. Not that it's all that complicated, but you do have to practice it a few times to get comfortable with it. Okay. All right. So so this is what we'll pick up with on Monday is completing the square to write an equation for a circle in standard form. All right. And then you'll get to practice that. And then we'll go on to our next topic. Okay. Which is going to be lines. In some sense, that's a little bit more comfortable because lines are easier than circles. All right. All right. So I'm going to stop the tape. So y'all going to get out a few minutes early here today. So enjoy the weekend. It's kind of cold outside, unfortunately. Let me stop.